Greetings, folks. Professor Fiore back one more time. We're going to take a look at bias stability in bipolar junction transistors. We're going to do some simulations on base bias and collector feedback bias and see which one is really the more stable of the two. We can, of course, extend this idea to other kinds of bias, but we'll just start off with these two, right? Base bias is usually the very first bias that we look at. It's very simple, very straightforward. Collector feedback is a very slight variation on it. It uses the same number of components, but is supposed to be somewhat more stable in terms of collector current. What are we talking about in terms of stability? Well, I'm going to focus specifically on the variation of collector current with changes in beta. How does beta change? Why does beta change? Well, first of all, the first thing we have to remember is beta varies from one transistor to the next. And that's true if we look at a specific model or we look between models. In other words, I compare, let's say, a 2N3904 to a 2N3055. We do not expect the betas to be the same. Secondly, if I just grab a bunch of different transistors of the same model, like a bunch of 2N3904s, I do not expect the betas to be identical under the same conditions. That's the first thing, right? So there's device by device variance. Secondly, we know that beta will vary due to external environmental factors such as the temperature. Generally speaking, as the temperature goes up, the beta is going to go up, okay? There are other characteristics we might consider along with that. Then there are circuit parameters. Beta will vary in accordance with things like the collector emitter voltage or the actual collector current. So all of these things play a role in setting exactly what the collector current is going to be via changes in beta, because beta is an important characteristic in determining the collector current. Why do we really care? Is it just because, we're like anal retentive about this whole thing? No. IC itself, the collector current, is very important because it sets other circuit parameters. As we will see in the future when we look at AC analysis, amplifiers for example, we will see that the collector current can affect other parameters, for example, something called R prime E, which will set or help set the voltage gain of an amplifier or its input impedance. It can also, the IC that is, can also help set what the output compliance is. In other words, the range of voltage it can swing before it starts to clip, before it starts to distort. Am I going to get 1 volt peak to peak out of this thing or 5 volts peak to peak? So making sure that the collector current is stable is important because that means a stable collector current will lead to stable circuit performance. If the collector current's varying all over the place, then my circuit performance can vary all over the place, right? I don't want to get an amplifier, find out that some of them have a gain of 25 and other ones have a gain of 37 or 18, right? We want consistency here. I don't want to have to go through a box of transistors and find, just the right transistor to get the kind of parameters that I want. So I would like the collector current to be pretty stable regardless of these changes in beta. Temperature goes up, temperature goes down. I'd swap out a different transistor, right? I'm going through a production run with thousands, tens of thousands, hundreds of thousands of transistors. I want to make sure that I always get the same kind of circuit parameter result, okay? So, finally, we asked the big question. How do we determine the collector current stability with regards to beta? One circuit topology compared to another one. In our case, a base bias and a collector feedback. And the key here is to do it fairly, because there's a little bit of a gotcha here, which we're going to explore. What you might think of initially is not necessarily the best way to do it. So let's take a look at our first contestant, a little base bias. So what I've done is I've got a simple base bias circuit here. I've just cloned it. Now I'm going to use two different transistors. I've got a 3904 and a 2222, only because I know that the models used here in the simulator have slightly different betas, right? Their characteristics are a little bit different. In lab, these are kind of similar transistors in that they're both small signal NPNs. 3904s tend to have slightly higher betas. You could, if you really wanted to, you could put an 04 and an 04 in here and then go in and actually change the parameters in the simulator for one of the two transistors. I just find it a lot easier for the sake of illustration here just to use two different similar kind of small signal transistors, right? All right, so the proof to find the collector current here is in the textbook, in the Semiconductor Devices textbook. And if you're new to these videos, I'll just throw out here, you can download those textbooks, all of my textbooks, the semiconductor book, AC and DC circuit analysis, the op-amp book, the microcontroller book using the Arduino. All of those things are free. You can get them in PDFs or ODT formats, download them, have fun with them, right? You can also get print copies on Amazon, whatever. Proofs are in there, so I'm not going to go through the proof. But just a really quick reminder. Let's take a look at the first circuit here. I got a 15-volt power supply, right? Connected up here. The emitter of this transistor is at ground. We know that if the transistor is forward biased on the base emitter, we're going to get about 7/10 of a volt here. Okay, a little bit more, a little bit less, but around 7/10. So that means all of the power supply less the 0.7 has to drop on the base resistor. So there should be around 14.3 volts across this resistor. And just using Ohm's law, you divide that by the 1 meg, we should have around 14.3 microamps. All right. Multiply that current by the beta, and that will tell you what the collector current is, as long as the transistor is in linear operation region. Right? If it's in saturation, all bets are off. These are in linear operation. There's no saturation, so that's all we have to do. So I just threw some values in here. Right? There's the 15 volts, 7/10 for the VBE. There's the 1 meg bias resistor. So we expect 14.3 microamps in both of these circuits for the base. RB1, RB2, we expect 14.3 mics. All right. Now, just so that we can kind of bookend our calculations, I don't know precisely what the beta for this device and this device are going to work out to, but I'm going to throw out some kind of low and kind of high numbers. So we'll tell very quickly if what we have makes sense. So I'm going to throw in a beta of 100 first. So take your base current, multiply it by 100, 1.43 milliamps. And then on the high side, I'm going to use a beta of 200. And you just do the same thing, and that works out to 2.86 milliamps. All right. What's the actual beta for each one of these? I don't know. Maybe it's 117. Maybe it's 198.2, 143.76. Don't know. All right. We just know that if we do the sim and we get a current like 15 milliamps or 12 microamps, we know something's messed up here. All right. So let's just do a really quick analysis, little DC analysis, and we'll see what we get. All right. So for our 04, we get 2.6745 mils. All right. That's pretty close to this upper limit of 200 beta. What's that going to work out to? 185, 190, somewhere around there, but, looks good. The 2222, where I'm getting a little bit less, 2.2729. So not down around 100, halfway-ish. Maybe that's going to work out to 160 or so, something like that, okay? But clearly we see what's going on here, right? These two transistors are going to have different betas. We see different collector currents. Now, I'm not looking at it here, but different collector currents are going to mean different drops across the collector resistors, which will mean different collector emitter voltages, right? These things just sort of multiply these changes, right? So this is step one. We can see that as the beta changes, the collector currents change, right? These two circuits are otherwise identical. Now let's compare that to the collector feedback. So basically the same circuit. All we're going to do is move one end of the base resistor. All right, so I take that resistor, instead of bringing it up the power supply, I bring it over to the collector. Now the basic idea here is, as the collector current would increase, let's say there was a temperature increase, Now, for some reason, there's an increase in beta, let's say, and that means an increase in collector current. As the collector current would go up, that means there would be a bigger voltage drop across RC. Now, the collector to emitter voltage is whatever the power supply is minus this resistor's voltage drop, right? Basic Ohm's law, KVL kind of expression. So as the current goes up, this drop goes up, which means that VCE has to go down. Now, VCE is comprised of two things: the base emitter drop, which we know is locked at about 0.7, and the drop across the base resistor. So basically, as VCE drives down, there is less voltage across RB. That means the base current is smaller. So that decrease in the base current tends to at least partially offset, or fight, however you want to look at that, the tendency of collector current to go up. So theoretically, this thing should be more stable. This is an example of what we call negative feedback. It's trying to stabilize the circuit. It's trying to come up with a nice set point, right? So you get too much current, increases the voltage on the resistor, which decreases this voltage, which in turn decreases this voltage, which decreases the base current. And again, collector current is beta times IB. So if IB is decreased, we expect IC to come back down a little bit, right? Whereas in the base bias, it's just 1-to-1. Whatever you get for base current, and that's fixed, boom, you get beta times that for the collector current. So this should be a little bit more stable. In the text, I developed this equation. I derived this equation. So again, I'm not going to go through it. Just going to plug the numbers in here. When we drive through here with a beta of 100, we get about 3.4 milliamps. When we do it for a higher beta of 200, we get 4.6 milliamps. Now in the base bias, when we did this, we noticed that the 2-to-1 beta variation produced a 2-to-1 current variation, right? I'll just go back to that real quick. All right, so beta 100, 1.43, beta 200, 2.86, right? 2-to-1 on beta, 2-to-1 on current. Okay, on the collector feedback, 2-to-1 on beta, we get less than 2-to-1, right? If it was 2-to-1, this should be 6.8. Well, this is theoretical. So what are we really going to get? All right, let's run it. So let's say you're in the lab and you're trying to investigate this on your own. Now, this would be a good lab experiment. There are some experiments that follow this in the lab manual that accompanies the text, where I have you get 3 transistors, right? 3 of the same. Go to the bin, right? Go to your transistor bin in the lab and grab 3 2N3904 transistors, put one in, measure the current, turn off the power, pull it out, put another transistor in, re-energize. What's the new current? Repeat the process with a 3rd transistor. What do we get, right? It's a really, really, really remote chance that all 3 transistors are going to give you the identical currents. All right, it's just that simple. It's a possibility, but it's not a probability, okay? All right, so let's do a sim and see what we get here, right? Again, we're doing this 100 to 200 to kind of bookend this and see what's possible, what's sort of realistic, all right? All right, so I'm getting, for the 04, we're getting a little over 4.5 mils, and for the 22, we're getting 4.2. All right, so that has collapsed down a bit, right? I mean, they make sense. This is below the 200. They're both above the beta of 100 with the 3.4. So that looks pretty good. All right. Now, how do you determine which one is, by which one, I mean which circuit, right? The collector feedback or the base bias, is the more stable circuit? Well, the simple way, which is really not a very good way, I would go so far as to call it the wrong way, is to simply do this. Take the 2 currents for the one, 2 currents for the other, figure out what the change in current is, right? So for the base bias, let's go back to the first circuit over here, right? We had 2.67, 2.27, right? 2.67, 2.27. just subtract them, and we find out, the smaller from the larger, and we find out we get a little over 400 microamps of difference. Do the same thing for the other circuit, the collector feedback, right? I got just about 4.55 and 4.23. Do the same thing there, right? There's the 4.55 roughly and the 4.23, and we get about 317 mics. Okay, don't need that anymore. You can see clearly this is a smaller number than this. It's about 80, a little less than 80% of this. So, what are you going to say? You're getting maybe, 20-ish% improvement. Okay. Whatever it works out to precisely. But you would say, well, yeah, okay, it's a more stable circuit, right? There's a smaller change in current. The problem here is, the reason why I would consider this to be an unfair comparison, right, is that the base currents themselves, and I shouldn't say base, the average currents themselves are not the same. These currents are sitting a little over 4 mils, 4.5 mils. These are sitting only around 2.5 mils. So, 400 mics out of 2.5 mils is a much bigger change than 300 mics out of 4.5 mils. All right? Does that make sense? You have to compare it against the base, the sort of foundational level, if you will. Okay? So what's the proper way to do that? What's a better way to do this computation? Well, you take the difference, but you compare it against, a reference. So for the base bias, I would take the difference, again, subtract those two things. This is going to give you that 400 mics, and then divide it by one of the currents. In which case, what we find is, at least compared to the max current, we find there's a difference of 15% on the base bias. When you do the same thing for the collector feedback, right, there's the difference divided by the first one, we find there's a difference of only 7%. So back here, it looks like, it's modestly better. It's a little better, right? Collector feedback is a little better. But the more fair comparison, we see, in fact, that the collector feedback is more than twice as stable as the base bias. This thing has a 15% variability. This thing only has a 7% variability, right? Simply because these currents are bigger, right? If you don't do this and you just go by the absolute change in current, then circuits that have small collector currents are going to necessarily look better than they really are, all right? So this is the kind of comparison you want to use. Back here, collector current, collector feedback looks a little better. Over here, it's a lot better, right? It's much more betterer. That's a technical term. It's much more betterer. I'm not going to say it's the betterer-est. There are circuits that are much more betterer-est than this. But, voltage divider, I'll throw that out, to supply emitter bias. But clearly, this is an improvement over this one, all right? And this is the way that you would do it. So any two circuits you want to compare, do it this way. Don't do it the other way. Make sense? I hope so. All righty, I think that covers what we need to look at in this video. So any questions, you know what to do. Leave the comments. And this is Professor Fiore saying, have a good day.